nanohub.org.
Hello, I'm Ryan Wagner. I'm a doctorate student in Professor Arvind Raman's lab group. I'm in the third year of my PhD, and a lot of my work has been on using FZ curves to extract material properties. So we started doing these experiments, and then we'd do the experiment, get one number, repeat the experiment again, get a different number. So we kind of had this question of, well, why was that happening? So in order to kind of address that, we started doing all this uncertainty stuff. So what I'm going to run you through today is just to, again, go over how to extract elasticity from a FZ curve. And then I'm going to talk about the uncertainty associated with doing that. And hopefully I'll show you a bit of a case study of some of the work I've done to try to highlight why is this important and what sort of bounds you can expect from this process. So I'm going to first off, hopefully just saying the grass is green here, I'm going to tell you again what an FZ curve is, just in case you didn't know. So we're going to start out. Initially, we're kind of far away from the sample. We will bring the sample into contact with the tip. There will be a snapped contact phenomena. We'll ramp up to some maximum force level. And after that, we'll withdraw, and then there'll be a snap out of contact phenomena. To kind of clarify on the coordinate system I'm going to use for the rest of the lecture, is just a schematic of the AFM system before and after this experiment. So before is the dotted line, so we're away, and then we push into the sample. I'm going to let Z be the motion of the Z piezo, delta be the deflection of the cantilever, and then D be the indentation into the sample. And I'll just use subscripts on Z and delta to tell you what units they're in. That'll become clear why I'm doing that later. And so I just want to point out in this experiment, what you fundamentally observe in the AFM system is the voltage input into the Z piezo, and then the voltage output of the photodiode. So we're going to observe these parameters, go through some sort of process, and eventually get elasticity somehow. To tell you again what that curve looks like is, again, I got the little numbers up there to try to show you where you are. Far away from the sample, snapped contact, which is 2, ramp up to some maximum force, withdraw, snap out of contact. And I'm going to let F be the tip sample force, D be distance, and then again Z piezo displacement with nanometers this time. And we're going to want to take that curve and convert it into a force distance curve, because that's how our models are. All the models are not F versus Z. All the models describe F versus D. So we need to do that process. And then eventually, by fitting a model to this FZ curve we get, or to the converted FD curve, we extract elasticity, which is our parameter of interest. So again, this entire process is going for some inputs, through some series of calibration, through some model, to elasticity. So as I understand, last time Professor Raman talked about how to calibrate these FZ curves. Really, there's kind of 3 calibration parameters that somehow we're going to have to come up with. We're going to need a nanometer to volt conversion for the Z piezo motion, a nanometer to volt conversion for the photodiode signal, and then a nanometer to force conversion for the cantilever deflection. I'm just going to call those calibration parameters CZ, CL, and CK respectively. So initially, again, we start out, we have our curve in volts per volt, and we want to go to nanonewtons per nanometer. So I'm just going to walk you through one method of doing this. So first, the Z piezo calibration. So what we can assume is that the relationship between voltage input to the Z piezo and displacement is linear. If we do that, we simply define a calibration, Z in nanometers equals a constant times Z in volts. And so we need to find this constant. You come up with several ways of finding this. One common way is to scan a sample of known height. Well, how do you get a sample of known height? Well, you have to measure it with something else. And you get into a series of, well, how well do you know the height and all those issues. But let's just say we have that sample, then we simply scan it, define a calibration. CZ is our reference height divided by whatever voltage we measure over this height. Now, of course, it's always a good idea to ask how good of an assumption this is. So what this curve is we have some other linear sensor that we've measured the displacement of the Z piezo in microns. Let's say we've measured it rather accurately. And then along the x-axis, we have our voltage input to the Z piezo. So this is what that curve kind of looks like over its full range. For specifically, this is for the Asylum MFP 3D AFM system that's over in Burke. So is that a good assumption, that this is linear? Well, it kind of depends, right? I mean, if we do our calibration over the entire dynamic range and just use this part of the curve, well, then we're going to kind of get an error. If we, say, do our calibration up here and then use this part of the curve, well, it's going to be a little off. But generally speaking, it's probably not a horrible assumption. It's reasonable, 10% sort of issue, maybe. Second calibration is the photodiode calibration. So to do this, one way of going about it is to assume that we have a stiff sample, do an F-Z curve on the stiff sample, and if the sample is stiff, we can say there's no indentation, D is 0, in which case we expect the cantilever and the Z piezo to move with a 1-to-1 ratio. So if we do that, we can simply define a calibration parameter, either CL in its dimensional form of nanometers per volt, or M if we want to talk in volts per volt, so volts of Z piezo motion for volts of photodiode output, or CL, which would be nanometers of Z piezo motion per volt of Z piezo output. If I'm saying that right, yeah. Or other way, sorry. Anyways, if we do that, we can get a calibration equation. It's just deflection in nanometers is equal to some constant times deflection in volts. That's supposed to be a delta. Or that's supposed to be a, yeah, it does look like a partial. That's what the Times New Roman delta looks like in PowerPoint, apparently.
Delta you defined the first slide.
Yeah. Yes.
In your MPAS, is delta CV, is that the same delta ZV from the piezo calibration, the CZ term, ZV?
Yeah, it's the same CV. So, I mean, it depends on what units you want to use. So if you want to do it, see, if you use CL, then your calibration is going to depend on your Z piezo voltage, and or Z piezo calibration. And that will become an issue when you want to talk about propagating uncertainties, because then you'll have a kind of a correlated type of effect, which can make things confusing. So it tends to be simpler to not have that dependence. And the way to remove that dependence is to simply do the calibration curve in volts per volts. So, I mean, when Professor Mon gave this talk, he probably said CL. I will prefer to talk about M, but I mean, they're just different by a constant, and that constant is CZ. Is that clear to everybody why that's the case? Okay. And, yeah. Then the last calibration we're going to need is for cantilever stiffness. So we need to convert cantilever deflection in nanometers to some force in nanonewtons. There's a rather large body of literature on doing this, and a lot of debate as to what is the best method and what are the various merits of a lot of methods. A few common ones are Sater's, which uses the hydrodynamics of the cantilever and its dimensions. The thermal method, which works via equal partition theorem. And then the Cleveland method, which you add a mass and then observe the shift in resonance frequency. For the purposes of my talk, I'm going to talk about using the thermal method just because that's what I tend to prefer to use. Using one of the different methods leads to slightly different kind of calibration paths. But anyways, the equation is simply, if you know the mean squared deflection of the cantilever, the stiffness is a factor times the Boltzmann constant times temperature divided by mean squared deflection. And this all should again be reviewed from what Arvin talked about last time. So let me just recap what this calibration path I kind of laid out is. So first, we scanned a sample of known height. We determined CZ, which was a function of our voltage from the photodiode and our voltage from the Z piezo. Then if we do an F-Z curve on a stiff sample, we can get CL, which is a function of, again, those photodiode piezo voltages and CZ. And if you, as I said, if you want to kind of remove that dependence from CZ, you can talk about M, so non-dimensional photodiode sensitivity. And then For KL, we measured the thermal oscillations of the cantilever, and that was dependent on cantilever deflection, our nanometer to volt conversion, CL, and T. So if you kind of notice you get this funny interdependence of calibration parameters if you do this in the common way. If you talk about, CL, CZ, and K, we've created a situation where CL depends on CZ, K depends on CL and CZ. So this, again, will become important when we want to talk about how to propagate uncertainties in these equations. And I also want to point out this is by far not the only way of doing this. One can imagine if we, for example, know the cantilever stiffness from one of the other methods. For example, if we just geometrically determine it with EI over L cubed, I think. Or if we use Sater's method, we could get KL. We could use the thermal method to get CL. And then we can do an F-Z curve on a stiff sample to get CZ. So, you can come up with various methods of doing this calibration, quote, path, and you get different results. And this will, again, have a different effect on how uncertainty will propagate. Because in this case, we've had uncertainty propagate from our transfer standard kind of to CL to K, whereas in the other case, we can propagate uncertainty from K to CL to CZ. Oh, and just one other practical note. In an AFM system, the cantilever is all the KL calculations are for the cantilever when it's like this, and Z piezo is like that. In reality, that is never the case, because if we try to bring the cantilever perfectly into the sample, well, we tilt a little bit this way, the back of the cantilever chip can hit the sample. So in practice, the AFM cantilever is tilted. So really, we have a situation where the AFM cantilever is like this, and the Z piezo is like that. And one can imagine we've kind of effectively stiffened the cantilever by doing that, because now it's kind of transversely, axially loaded. And this guy by the name of Hutter, who was also the guy who did the original thermal calibration stuff, worked out that the one simple approximation for that is just dividing by cosine squared of the cantilever tilt angle. So this is like a 20-30% effect. So it's just a FYI, if you do these curves, this effect is there. If you really care about getting the correct force, you kind of need to account for this. Just a comment. So we've got our force displacement curves, our F-Z curve. We have our axis in nanonewtons per nanometer. So now what do we do? As I kind of mentioned earlier, F versus Z is not incredibly useful. If we were going to write a model, why would anybody write that model in terms of sample position versus Z piezo motion? Now, if you're writing a model, you're going to want to talk about gap or indentation between the AFM tip and then your sample surface. So there's kind of two, if our ultimate interest is extracting, say, elasticity, there's kind of two approaches we can take. One, we could transform our model from F versus D to F versus Z, which is probably kind of complicated to do. Or we can transform our F-Z curve from F versus Z to F versus D, which is actually rather not complicated to do. Because, again, if we have an infinitely stiff sample, we expect our Z piezo and cantilever to move with a 1-to-1 ratio. If our sample becomes softer, we expect the Z piezo to move more than the cantilever deflection. And that difference is going to be how much the sample is being indented. Well, the combined indentation of the AFM tip and the sample, but for practical purposes, usually it's assumed that the tip is considerably stiffer than the sample. So we simply get the formula that indentation is D, which is Z in nanometers minus cantilever deflection in nanometers. And then we can kind of easily convert that back to our fundamental observables, which was voltages, by replacing Z in nanometers and delta in nanometers. So we can have CZ, ZV minus CL DL, or delta L. Well, then we can also go one step further, and we can replace CL with MCV, factor out MCZ, factor out CZ, and we're left with this equation. Oh, sorry, go ahead.
That applies for any type of tip, whether it's round or...
Yeah, this is true in general. We've measured...
You don't have to make any any adjustments because you are using a round tip or a pointy tip like a triangular?
For small indentations, definitely not. If you want to talk about very large indentations, well then, I imagine the situation could perhaps come more complicated because the indentation could be significantly different as you move along the tip.
Yeah, but by and large, I mean, 90% of the cases so far, tip geometry doesn't play a role.
Yeah, I would say I can't think of a case where where that would be an important issue. But
so that issue will come. Geometry comes in later.
Yeah, the tip geometry is more included in the model. So if we consider measuring indentation as the apex of the tip indenting into the sample, and if we have the laser spot directly over the apex of the tip, this is fine. But if you want to talk about, one can imagine a situation where this could become more complicated. If you say you have a funny shaped tip, maybe your tip is not a hemisphere, but for some reason it's a double tip with two kind of separated hemispheres and something funny.
Let's not look at the extreme cases. The question is, so far in the standard procedure, you don't have to worry about tip geometry.
Yeah, so far tip geometry has not been taken into account.
Or it doesn't need to be.
Doesn't need to be, yeah. So that is D. Any other questions? No? Then we also have F, which we can write in terms of our observables and calibration parameters, is KLCL delta V over cosine squared alpha. And just graphically demonstrating this, so this is our F-Z curve in deflection in nanometers per sample displacement in nanometers. A stiff contact would look like this black line here, which is at a 45-degree angle. And this difference between our F-Z curve on a stiff sample and our F-Z curve on a soft sample is our indentation. And if we subtract that and plot it, we would get a curve that looks something like this, where far from the sample, distance and displacement are the same, and close to the sample, we have a case where they're just subtracted. So we have an FD curve in force per nanometers, and we're trying to get to elasticity. So the next step is we need some model of that F versus D curve. In general, there are many types of models. One can imagine very complicated molecular dynamics. There's finite element simulations. Or perhaps simpler, we can just talk about analytical contact mechanics approaches, such as the Hertz solution, which you guys have talked about that, right? Talked about Hertz. DMT, talked about that. Yeah, and then JKR, Sneeden, there's a whole list of these kind of solutions. But bottom line is you're going to have force as some function of D and the material properties and the surface geometry. And the example I'm going to talk about is the DMT model. I'm not going to try to say those guys' names so I don't slaughter the pronunciation, but those are the guys that wrote the model. And talking about that one. So DMT is simply a modification of Hertz contact to include adhesive forces. So the model is going to look something like force is equal to a constant S, which is related to tip sample properties and geometry. So properties such as elasticity, which is what we're trying to get to, Poisson's ratio, and surface geometry such as the radii of curvature of the sample and radius of curvature of the tip. And then we have another constant, which is just the intermolecular distance. And then our fitting parameters, because what we're going to do is we're going to take this model and we're going to fit it to our data. So our fitting parameters will basically be indentation and our maximum adhesive force. So we have two fitting parameters in this case. And then if we want to kind of go a little more into what our maximum adhesive force is, we can kind of relate that to work of adhesion between the tip and the sample, which is not a material property, that's a system property. But it gets kind of tricky to relate that to surface energies. You run into issues where the surface energy of the tip is much, much higher than the surface energy of the sample, so it gets complicated. I don't know of any real works that have done this particularly well. I don't know.
Which part of it?
Going all the way from work of adhesion to surface energy. So Does everybody know what the difference between that is? Work of adhesion is equal to surface energy. If you have three, if you have a surface, another surface, and a surrounding medium, the work of adhesion is equal to the surface energy of the surface plus the surface energy of the other surface minus, or no, never mind. Don't worry about that. I wasn't planning on talking about that anyway. But if you want to read up on that, Israeli is a great reference for getting into that. Yeah, the Dupre equation. I was saying surface energy when I meant interfacial energy. So
in theory, using the Dupre equation, you can calculate the interfacial energy between a crystal and a motor.
Well, you would have to know, but you'd have to. There's W equals the three interfacial energies added, first two added, last one subtracted. So you'd have to know what two of the three interfacial energies are to calculate the third, which is an issue. There's an approximation which says it's only dispersive forces are present, that work of adhesion is equal to the square root of the product of the two surface energies. But for the case of AFM, usually you have a tip, which is silicon, and the surface energy of silicon is much larger, on the order of joules per meter squared, whereas the surface energy of a lot of, say, polymers or common things you would measure is much lower, on the order of millijoules per meter squared. So you kind of got a funny situation where, as far as I know, I've not seen any works that have done that particularly well.
Yeah, the standard thing is just to plot the adhesion force and not really convert it into a fundamental material property like work of adhesion or surface energy.
Yeah, essentially we tried to do that, but in some of the work we did, but we didn't really believe the numbers. So I advise just leaving it as work of adhesion, which is a system property, not a material property. Any other questions on this?
So, you're measuring the mechanical properties using a model. It's not like a typical test where I take, the slope of the curve and I found the Young modulus. You're using a model, a mathematical model, to get the material property.
Well, saying that the slope of that...
It will depend on the model.
Right, but I will point out that saying your slope is linear in a stress-strain curve is also a model. It's just a much, much simpler model. In this case, we're forced to go to more complicated models because our system's not so straightforward. It'd be great if we could just take this nanomaterial and do a stress-strain test on it, but how do you pick up a material and measure a stress-strain test? It's not really... Well, I mean, there's clever ways of doing similar type experiments, but this is probably the simplest way to get to these numbers, and using these numbers involves modeling the AFM tip and indenting the material. So instead of a simple linear stress-strain curve, we now have this F-Z curve, and the model is just more complicated.
May I ask one more question?
Yeah,
okay,
please.
For the DMT model, right?
Mm-hmm.
And there is another one, JKR.
JKR, yeah.
And in your opinion, DMT is a better approximation of JKR? I don't take into account Hertz because Hertz doesn't take into account interactions.
Right. There's a kind of a really good work by Johnson. Probably, if you want to ask me after class, I'll probably dig it up for you. But it explains the difference between JKR, DMT, and Hertz. Essentially, they're different ranges of a solution. So Hertz is valid at very high loads when the adhesive force is negligible. DMT turns out to work well for very stiff samples. JKR works better for softer samples. And there's another guy named Moji who did the area between JKR and DMT and showed it was kind of a linear variation of this of a parameter. So really, they're just opposite extremes of the situation. So it depends on which your sample is as to which is more appropriate. But I will say it's far more convenient to work with DMT because it's actually simpler than JKR in terms of doing this type of analysis I'm going to do.
Just to close my idea. So with the DMT model, what I am doing is, at the end, I am feeding a curve.
Mm-hmm. Yeah, at the end of the day, we're going to fit a curve.
Any fitting to F-Z or fitting to curve.
Anything else? Okay. So Professor Rahman told me that you guys simply talked about, when you did these, you talked about sphere-plane interaction. He told me it would be a good idea to kind of talk about more complicated systems. So in general, you can expand Hertz or DMT into the situation where we have an ellipsoid interacting with another ellipsoid. So I'm just going to briefly run through, this is kind of a lot of equations, but I'll just briefly run through and kind of point out some main points for this issue. So let's consider the case where we have an upper ellipse described by two radii, say R1 and R2, and a lower ellipsoid described by two additional radii, say R1 prime and R2 prime. So what this is going to do is, once we have this, if you think back to the Regius slide, we had that constant S, which was surface geometry, material properties. That turns out to be related by the first equation here, where these that E tilde and K tilde are the elliptic integrals, which are simply a function of this parameter Kp. And Kp turns out to be just, you have to solve it finding this equation. It's not really a very physical quantity. It ends up, when you start working with these models, it's just kind of the way it goes. So you get your parameter Kp from the bottom equation, plug it into the top equation, and eventually you essentially relate S to, these are all geometry terms, another geometry term, which is the inverse reduced radius, and then your inverse equivalent elastic constant, which those are just given as this term and this term. And so bottom line, if E is much, much greater than E tip, so in other words, if this term is essentially 0, they essentially get S is proportional to E, more or less, times some big geometry term that's all complicated, but basically it only depends on what all your radii are. So if you know all your radii, you plug it into this equation, you have a relationship between your curve fitting parameter S and E. And just to simplify that, for the common cases in AFM, say sphere, sphere, so our tip is a sphere and our whatever we're indenting is also a sphere, that complicated constant reduces to 4/3 times 1 over our tip times 1 over our sphere surface inverse. And then for sphere plane, it simplifies further because we can just let R of the surface, go to 0, and you just get 4/3 square root R tip. So that big whole complicated thing reduces down rather nicely for these situations. But for your reference, if you want to do something more complicated, you have to figure out the equations on the previous slide. And I think I give the reference at the bottom of that slide. Yeah, Borsai, 1987. Any questions about that?
What exactly is KP?
What?
What exactly is KP?
So it has to do, in all these we're going to assume, the model starts out assuming that the contact area is shaped as an ellipse. So Kp has to do with the ratio of the kind of axes of the ellipse. I don't know if it's the ratio of major axis to minor axis or minor axis to major axis, but I think that's the physical interpretation. I'm not pretty sure that's right. You probably want to double, if you're really, really curious, check that reference. But I think that's what it is.
And just to point out that, the question was also before, beyond this also when you have large indentations, these are all good for, DMT is always good for just small indentations.
Yeah, these are all small indentation models.
The large indentations, the overall, geometry of the tip beyond just the elliptical description or the spherical description comes in. Could you say a word about what those models are? And
Yeah, well, so in my case, I'm always interested in small indentations. So when I mean small indentation, what do I mean? I mean that the contact area is small relative to kind of the critical dimensions of whatever you're indenting. In cases where this is not the case, which is especially true in nano indentation, they often use the Sneeden approach. So you have larger forces, so the adhesive forces are no longer so important. So you go back to Hertz. The generalization of Hertz for any shaped tip is called the Sneeden model, which is an axisymmetric punch indenting a plane. And they do something called the Oliver-Farr approach, where they indent way into the sample and then let the sample relax and then withdraw and measure the force very carefully. And so really what happens when you go to much larger indentations is you deal with that model instead of the model I'm talking about, which is DMT. Does that make sense? So, curve fitting procedure. So, we have our equation. If you think back, it was F equals S, D minus something to the 3/2 minus something else. Really, if you're going to curve fit something, it's much more convenient to curve fit a line. The line is the simplest thing to curve fit. So if you can linearize a model and do a curve fitting, that is the way to do it. In this case, for the DMT model, and this is one reason the DMT model is, I say, a convenient choice, is it can be relatively easily linearized. So if you define a new D, call it D star, which is simply equal to D minus our A naught to the 3/2, you get a linearized model. So then it's simply a matter of using linear regression, which that's all these equations are. It's just the linear regression equations, and fitting your model. One complication that is worth mentioning is we said that D is Z nanometers minus delta in volts, right? So I asked you, what is the zero location of Z in nanometers? Where is the zero location of your ZPs? Minimum force? Anybody else?
For Z, you said.
Yeah, for Z. What is the zero location of Z?
Doesn't matter, does it?
Well, if it doesn't matter, then I can make D whatever I want it to be.
Right, but ultimately you just take the Z numbers, whatever they are, and make these, and then choose the Z to be 0.
Right. Yeah, I mean, that's what you're going to do. So ultimately, Z is arbitrary. D is arbitrary to a model. So if you have a model, that will determine where your 0 and D is. So you need to choose Z such that your 0 in your model is the best 0. Well, how do you get to the best 0? I mean, you can look at the curve and try to pick a point, but that's kind of slightly arbitrary. I would suggest using a method that, I should have put the reference up here. There's a couple guys that suggested this method, probably 2000, 2001 or so, of using the R squared value, which is just the goodness of fit parameter. So if you choose your model fit such that the R squared value is best, let that determine where your 0 location for D is, which I feel like, well, probably not a perfect way of doing it, is better than, pointing and clicking and guessing where the 0 D is.
But let the 0 location be a part of the fitting.
Yeah. Well, it's not really part of the fitting process. It's kind of separate from it in the fact that we're saying that we're going to maximize R squared. So choose D equals 0 such that R squared is maximum. So what you can do is do many fits for all D, or all choices for D equals 0, and then choose the one with the highest R squared.
Is small d a positive or a negative number? Because it seems to me it could be either.
Well, for this case, obviously that D minus A naught to the 3/2 can't be negative.
Right.
And that arises from the fact that DMT is a contact model. DMT itself says nothing about what happens prior to contact. When you start talking about DMT prior to contact, usually they say that van der Waals forces saturate, and then there's a transition to the DMT model. So obviously this equation is valid only when D minus A naught is greater than 0. So the way you address that is you just simply, when you're doing the curve fitting, the values where this is negative is essentially nonsensical. It's not part of the region where the model is valid.
But if d is equal to 0 is the minimum of the DMT, right? Then aren't all the values of d negative?
Well, it depends which way you define positive. The model defines positive D as, or I've defined in the model when I'm using this, positive D is more indentation.
Okay, well,
So,
I'm thinking of
oh.
the opposite. Negative D is...
Yeah, this is an issue that...
D is gap, and so when it's negative, it means we're in there.
Yeah, a lot of the contact mechanics models are this way. I think Veda, since it was developed from more of a van der Waals point of view, right? It's the other way. So, yeah. I guess we should have talked about this beforehand. I could have switched that. But yeah, in this case, D is positive towards the sample. Apologies.
Point, operationally, whether d is positive or negative, You take the absolute value and put it into this equation, operationally?
No, operationally, can I write on the board? Is that okay?
Yep.
So in reality, it's something like that, right? Operationally, this is the minimum, right? So we only consider the points on this side of the curve when we're doing our fitting. Because considering points on the other side of the curve gives us an imaginary value.
Flip the F versus D.
Yeah, well, it just needs to be this way. I mean, D positive has to be more indentation, the way I've wrote it. You could just as easily throw a negative in that equation and write it the other way. It would be perfectly fine. If I would have known that, if I would have remembered that you guys did it the other way, I would have switched it. Sorry for any confusion. So is this clear to everybody? All right. So we do the curve fitting. Let me just take a step back for a second. So we've done the curve fitting. And at the end of the day, we have all of our inputs to the curve fitting. I'm going to say it's 2n plus 11 or 2n plus 8 for this particular DMT model, where our inputs being all of your FC data pairs, so each FC data point, and then all of our calibration parameters, CZ, M, KL, and alpha, and then all the parameters in our model, which is our radii, or elastic constants. So elastic modulus Poisson's ratio, because we're doing it for an isentropic material. So one way to think about this process is that we have a data reduction equation that goes from our collection of inputs, which for uncertainty propagation reasons, it's good to have independent, to an output, which is elastic modulus or work of adhesion. Now I'm just going to briefly show you an example of some of the work I've done. This is for a material called cellulose nanocrystals, which are just nanofibers that are 5 to 10 nanometers in diameter, and then a couple hundred nanometers to a couple microns long. And so there we have an experimental F-Z curve. And we do the process I've been describing for the DMT model. And then we use the model of a sphere cylinder, so we have to use all those complicated KP equations and plug in the correct radii. This particular F-Z curve would then correspond to E equals 10.3 GPa. So we did all that, and we got a number. And
The distance in that plot is really indentation.
yes, it is indentation. I've always been confused about what the best word for this is, because before contact you have gap, right? And after contact you have indentation. I've kind of been using distance as both of those. One can debate what the best way to go about it. But yeah, I mean, if you want to call that indentation, that is indentation. So we got a number. That's great. What does this number mean? Yeah.
Over there, the blue one is the retraction.
Yeah. Yes, the red is the approach, blue is retraction. For the data processing, I would suggest just always using the retraction curve, because the retraction curve covers more of the interaction potential. Because if you think back, I believe this was in, Professor Amon discussed this, but there's regions of for the way the system is designed, there's regions of the FD curve that are inaccessible. It turns out that the approach curve has a larger inaccessible region than the retraction curve. So you can get more data, and more importantly, you can cover the minimum force value by using the retraction curve. So just an issue of practicality.
So while we're here, right, you get E from fitting the red curve to the data.
Yeah, E from fitting the red curve to the black dots.
W comes from what?
W is also, there's two fitting parameters, right? You're fitting a line, you have a slope and an intercept. E comes from the slope, W comes from the intercept.
Okay, so in the force versus Z curve, right, W comes from the minimum value of the blue data.
Yeah, so it's just a different way of, there's two ways to find the minimum, right? One, you can just take the minimum. The other, you could take the minimum from the model. I guess it's debatable as to the relative merits and disadvantages of doing it both ways, but you should get roughly the same answer. And again, my concern is usually more elasticity than work of adhesion, because work of adhesion isn't a material property, so I'm not quite as concerned with it generally. Anything else? Okay, so we have a number. What does it mean? So this is the example I came up with. So say, Doc measures the flux capacitance of something to be 7 and 30. Well, is that an agreement or disagreement? And the answer is, if the lab tells you that one value is 7 and one value is 30, you have no idea whether those numbers agree. I mean, one say, well, obviously 7 is much different than 30, but no, it depends on what the uncertainty associated with each of those measurements are. If you compute the uncertainty and get, a kind of a distribution of values, looks something like this, well then clearly 7 and 30 disagree. They're different numbers. But if we get, something that looks like this, maybe they're in agreement. Maybe we're not quite disagreement. In fact, for a probability distribution, you can say what % confident you are that these numbers agree. So I think this is, if you want to compare data quantitatively, this is an important exercise to go through. So briefly, just some nuts and bolts. There's kind of 3 common classification systems for uncertainty. But probably the classical definition is splitting it into random and systematic, where random is an uncertainty that varies over the course of your experiment, and systematic is an uncertainty that does not vary over the course of your experiment. Whether something is random or systematic depends on your definition of what your experiment is. So if you do, say, 1 FZ curve, different things will be random and systematic as opposed to if you did 100 FZ curves. So it's kind of, there's a little ambiguity in that definition. Another kind of approach to another classification system used by the verification and validation guys, this is done for a lot of simulation stuff, is aleatory and epistemic, where aleatory is, if we have a model, aleatory is variation in the parameters of the model, and epistemic is variation in the form of the model itself. And then there's kind of a standard guide for expressing uncertainty in measurement called the GUM that the ISO puts out. And they recommend using type A and type B to classify uncertainty, where type A is simply an uncertainty evaluated by statistical means, so in other words, sampling, and type B is evaluated by other means. And they specifically recommend this classification to get around the kind of the ambiguity associated with random and systematic in change of experiment. But I'm not going to exactly listen to the GUM and talk about random and systematic, because I think it provides a little additional insight if you use it correctly. So if we have an uncertainty and say an input parameter to a model, so an aleatory uncertainty, how do we equate that to an uncertainty in the output of the model? There's several methods for doing this. The one the GUM recommends, so the standard guide recommends using Taylor series uncertainty propagation. So we're simply going to take this equation and say that the sum of the uncertainties is the partial derivative of your data reduction equation f with respect to that variable times the uncertainty in the variable squared, and take the sum and then take the square root. To go from random and systematic uncertainties, I don't know what's up with my mouse. There we go. To go from random and systematic uncertainties to this combined standard uncertainty, which is again, just terminology from the GUM. It's just the square root sum squares of those as well.
What's the GUM?
Guide for Expression of Uncertainty in Measurement, the ISO standard for doing this. And then we can treat, if our sample's large enough, U is essentially a standard deviation. We can treat it like that, which is associated with a probability distribution function. And then based on our number of samples, we can go from our standard uncertainty U, which doesn't have an associated confidence interval, to expanded uncertainty, which is what capital U is. Capital U, which describes the uncertainty within a given confidence. So if I know capital U for the 95% confidence interval, that means I'm 95% certain that the true value of our measured variable lies within our best guess plus or minus capital U for the 95% confidence interval. And if your sample size is large enough, that kx term is 2 for the 95% confidence interval. If your sample size is smaller, you start dealing with distribution tables. So for the specific AFM experiment we're talking about, we can kind of consider that data reduction equation I was showing earlier as looking something like this. So we have a collection of what I've defined to just be input parameters. So our sensitivities, our calibration, so CZ, M, K, sorry about that. And those are all what I've green, so I can define all those as input. We're going to go through that process I discussed earlier, which was using the curve fitting procedure, the DMT model, the data collection. So we do all that, and we get to our elastic modulus, which is blue. So what this chart represents is how the interrelationship between those parameters. So if we apply Taylor series uncertainty propagation and choose the green parameters as our inputs, all the green parameters are independent from the other green parameters, which means that Taylor series should work okay. If they were not independent, then there would be issues with using Taylor series. So we can kind of think of this process as we know. We identify our input parameters, we propagate them, we kind of see what the important parameters are, and based on that analysis, we can go back and try to improve our experiment. Is it clear what I'm saying here? Does this chart make sense to everybody?
I think it would be nice to sort of point out, give a brief overview of where the uncertainties are creeping into the modulus measurement. If you can just go over from this chart, just to give an idea.
I kind of got that in some later slides. But yeah, so keep in mind this chart, and then a couple slides down the road, I'll start telling you, what the uncertainties in these input parameters are. So again, summary, if we just take the Taylor series uncertainty propagation formula, and we take that DRE we constructed for our independent variables, we get estimated a standard combined uncertainty for E as this equation. And so this is a bunch of parameters, right? Turns out some of these will be very small and they can be neglected, and then some of these will be very large and they'll be important, and those are the parameters that we can really use to try to improve our experiment. So again, it's just the square root sum squares of the uncertainties for all the inputs. So, what are the uncertainties in the inputs? This is just an example for 4 of the parameters, specifically CZ, KL, and M, because I'm trying to make them independent. So this is just a step height measurement of a sample that we know the height is 8 nanometers plus or minus 1.5 nanometers. And then we measure the voltage on the bottom surface, voltage on the top surface, get a PDF for each of those. And then we can, again, just use Taylor series uncertainty propagation to combine them. And we get an uncertainty for CZ. And for this particular experiment, it turns out that we found CZ to be 13 plus or minus 3 nanometers per volt. So that's about 7%, something like that. Then for K, we've done what this slide is showing is found the area under that curve is the mean squared deflection. Why that is the mean squared deflection is complicated. I don't really want to talk about it too much, but if you're really curious, you can ask me after class. So if we just compute the area under that curve, we repeat the K calibration many, many times, and we get a distribution for K. In this case, our distribution was 2.1 plus or minus 0.04 Newton per meter. which is about 5%-ish, something like that. And then lastly, the bottom, the red curve over here, shows our collection of about 100 F-Z curves on mica, which is our stiff sample. And based on all those fits, we get a distribution for M. And that distribution was, I think, 6 plus or minus 0.03, which is about 3% uncertain. So, and then the last one shows an SEM of the tip. And what you can do is you can kind of fit a parabola to the outline of that tip and then compute the curvature at the apex. And that will give you an R tip term. And based on how well that fit is, and you can come up with a rough approximation for what the uncertainty in R is. And I think that was about 10% as well. So recap our relative uncertainties for this particular experiment. This is just a case study that I've done, writing a paper on currently. Our uncertainty in CZ was about 10%. Our uncertainty in KL was about 5%. Uncertainty in M was about 3%. And then our uncertainty in our tip was about 10%. And notice this is only the aleatory uncertainty. I haven't talked about, well, the DMT model is not perfect. Turns out that's a much more complicated issue to address. So we do all this. This is just the same cellulose nanocrystal I was showing you before, where we showed one F-Z curve. And the value from that F-Z curve was 10.3 GPa. Well, now I'm going to collect 100 F-Z curves. For each F-Z curve, I can compute a combined standard uncertainty for both E and work of adhesion. I can come up with some fancy way of combining all those, such that we get a PDF for the total distribution of E. And then we can kind of come up with an estimate for what our variation is in E. So in this case, we found that our mean value of elastic modulus was 7.9. Then our 95% confidence interval varied from 3 to 22 GPa. So it's a lot of variation. So what this means is that if we make one measurement and we get 12, we make another measurement and get 7, well, those measurements are still in agreement because they fall within our 95% confidence interval rather comfortably. So, to break it down even further, we can take just an individual F-Z curve. This is the same F-Z curve I showed you a while ago. Just all of our inputs. And then if you think back to the Taylor series equation, we had the df, d, if we let xi be our input, dxi times uxi squared term. We can write out what all those parameters are. And then we can kind of identify which of these parameters are largest, because this is the largest contributor to the uncertainty in E. And we show that actually for this case, the non-dimensional photodiode sensitivity, which was 3% uncertain, turns out to account for basically 90% of the uncertainty we're observing in E. So, why is that? This is my last slide, but I write it on the board here. So essentially, what we've shown is that the sensitivity is really high for this M parameter. And does anybody have any guesses about why that might be? Okay, let's think back to what we did, right? So we took our FD curve and we linearized it, right? So we had that F versus D star. And we had some line, right, that we fit to data.
Well, I thought D was 3/2.
Well, D minus A naught to the 3/2, but same thing. And we fit to a line, right? So let's take one more step back. If we thought about how we got to D, we had our F-Z curve, right? Or this would be a 45-degree line, right? And then we had with some constant offset. I'm not going to draw the offset, but we got our curve that looks something like that, right? And we had this value. This was D, right? And then the equation for D, in terms of calibration, was D equals CZ ZV minus and delta V, right? And our cantilever deflection in nanometers is kind of a, let's just design that as a relatively large number compared to D. Our Z piezo displacement in nanometers is a relatively large number compared to D. We essentially subtract those two, and we get a small number. So we have two large numbers subtracted to get a small number. And then in terms of calibration, M changes all values of dV independently of, or all values of delta V independently of ZV. So that causes this entire curve to shift like this, which shifts our entire slope of this curve. And if you think back, I remember I said basically E was more or less proportional to the slope. So it turns out that because of the way we set up the calibration, M is the dominant contributor to uncertainty. So that's more or less the entire lecture I had planned out.
So the key point is, for many materials, when you do FC on a calibration surface, a really hard surface, we expect this 45-degree line, and you do it on most materials, polymers including. The FZ curve you get on the polymer is not going to be very different from the 45-degree line. It'll be a small change, and then when you do the FZ to FD conversion, you're basically subtracting Z and delta. Delta is again due to deflection. Both are, Z is in tens of nanometers. Delta can be tens of nanometers. So you're subtracting two quantities that are, rather large, and you're trying to get an indentation, which typically in this case may be 1 nanometer at most, or half a nanometer. So the uncertainty comes from that primarily, because if you haven't done your volts to nanometer conversion accurately, it just feeds into all this uncertainty into your final answer for the elastic modulus.
Yeah, this is kind of a situation that's unique when you're talking about a couple or less than a nanometer of indentation. If you start talking about larger indentations, for example, an experiment on cells where maybe it's 500 nanometers of indentation, it's not such a huge issue. It's kind of unique to the case study that I've done. Yeah.